And we'll turn things over to our final speaker, Nathan Walker.
Hi, everyone. Thank you for being here. It's been kind of a long day, so I appreciate your attention. I'll try not to make you all wait here too much longer before we can go eat dinner and relax. And before we start, I press something. Okay. But should be good. Before we get started, I don't really know anyone here, so I'm going to introduce myself. My name's Nathan, as she said, and I'm a graduate student at Oregon State University. And yeah, so I'm going to talk about utilizing resources efficiently in simulating gamma ray bursts. We've heard a lot today about multi-messenger astrophysics, gravitational waves, kilonova, supernova, and I'm going to talk about gamma ray bursts. And what they are is a transient signal of very high energy photons. So if we look at the sky, we'll see a burst of photons, literally a gamma ray burst that lasts anywhere from like 2 seconds or less, all the way up to a couple hundred seconds. That's called the prompt emission of a gamma ray burst, and it's pretty much like the proper gamma ray burst. And then following that prompt emission, there's an afterglow that can last anywhere from like weeks to months. So the whole gamma ray burst transient can last a little while, but it's still a transient signal. Once it's gone forever. And if you look at the right here, I have two pictures. They're artist renditions of two different progenitors that can produce gamma ray bursts. At the top, we have what is a depiction of a binary neutron star merger, right when the two neutron stars collide into each other. Due to the very strong gravitational forces, material from the neutron star gets pulled apart, forms an accretion disk, and that accretion will like feed onto whatever compact remnant remains from the neutron star merger and launch jets outward. And it's these relativistic jets that go outward that end up producing the radiation we see. And down here, we have a rendition of a star with a jet boring through it. What's hidden is if you look in the star, to the best of our knowledge at least, there's going to be a compact object and an accretion disk. And again, accretion is going to feed onto that compact object and launch a jet that pushes outward, and that produces the radiation we eventually see. They were first discovered in the 60s when we didn't really know anything about them. We didn't really expect to see them. And ever since then, they've been in one way or another a mystery. I've already talked about the progenitors. It took a long time before we could get to a place where I could talk about what might produce them. Part of that was whether or not they were of cosmological origin or whether they were in our own galaxy. I'm kind of going through a lot of history, but it turns out that they are by and large of cosmological origin, so very far away, and energetically that leaves things like this and very few others that could possibly produce them at that high energy. And what I focus on most of the time is what's called the emission mechanism, which turns out we still don't know, even though it's been like 50 years or more. So what I do is I run a bunch of simulations to try to figure out what's actually going on in these jets to produce radiation that we see. And to kind of put the computational challenges into context, I'm going to just briefly go over the process of how we simulate these and what kind of complications, technical problems can come into play. So the first step is we have to simulate what's going on at the progenitor level. So here I'm talking about compact mergers. I could also have a slide about supernova. But here we have time snapshots of a binary neutron star simulation. Here's the top view and here's the side view. The paper that this comes from simulated the first 100 milliseconds after a binary neutron star merger. So it started before they merged and let it merge. And waited to see what would happen after 100 milliseconds. And just that physical 100 milliseconds took a very long time to simulate. The type of simulation we needed for this, or I didn't write this paper, but it's called a general relativistic magnetohydrodynamic simulation. It's hydrodynamics, so fluids, and then it takes into account general relativistic gravitational effects. It takes into account magnetic fields and plasma and all sorts of stuff. If you pile all of that on together into one simulation, it takes a very, very long time. And added to the fact that these simulations were done in 3D, 3D simulations also take a very long time. And at the end of the simulation, if you look at the remnant, you see something like this. Down in the center is a what's called a hypermassive neutron star. So more massive than neutron stars typically get. And we don't know yet if real compact mergers collapse directly into a black hole or if there's an intermediate stage where it's a hypermassive neutron star. But in this particular simulation, it was a neutron star for a little while. And these coils are magnetic field lines. And the fact that the magnetic field lines are coiled in this particular way, oriented away, kind of like the jets we saw on the previous slide, this is essentially what allows jets to be launched away from the compact object as things accrete inward. So that's one stage. If we move on, here's the kind of stuff that I focus on, which is the jet at distance further away from the black hole and the radiation that happens in them. On the left is just a bunch of information about this kind of simulation, about this particular simulation. I won't talk too much about that. I just want to mention that in going from the previous slide to here, we dropped the general relativistic part, which this is still relativistic, but it's special relativistic, which is simpler to run. And we also only ran a two-dimensional simulation. So these cuts are basically the only details that mattered as far as the computational cost went. We didn't have to take into account any asymmetries relative to the jet axis. And those are necessary because if you, it's hard to see here, but the length scale on this top row is 10 to the 9 centimeters, which is already a few orders of magnitude beyond the scale we saw on the previous slide. And the further we go down these rows, the bigger the scale gets. So here it's at 10 to the 13 centimeters. So to be able to run simulations this big, we have to get rid of details. So we get rid of general relativistic, magnetic phenomena, and anything like neutrinos or whatever. So once we have a simulation of a jet that's sufficiently far away from the compact object, we start to do radiation. And to do that, we take hydrodynamical frames like the ones I just showed you, and then we literally just inject photons into them and let them scatter. After hearing some of the talks this morning, I think this would be a pretty good opportunity for high throughput computing. Each of these photons don't really care at all about anything besides where they're at. So if you could figure out ahead of time where the photons are, keep data from the hydro frame kind of around that, you could easily distribute it like each photon on its own core and just do whatever you guys do, which I don't really know. So. And here's just a flow diagram of the process of actually scattering these. You have to sample the region around where the photon is, figure out what the mean free paths are. From those, you can figure out whether the photon should scatter or not. If it does, scatter it. If it doesn't, let it propagate and just kind of continue that over and over. These photons are going to scatter in the jet in this frame for like a very long time until they until the simulation goes long enough that they go into the next frame, and it's going to repeat that process for all the hydro frames I showed you. So just really quick, I injected photons into this frame. I just showed you where they were in this frame, and they're just scattering all the way from here until here, which took quite a while to get done. So really quick before I start talking more about the computational challenges, this is just the kind of things we get from doing that whole process. This is a light curve, which looks pretty typical for gamma ray burst light curves, and this is a spectrum. I could talk a lot about what I would like the spectrum to look like instead and what's good about it, but That's really not the topic of this talk, so I'm going to move on. And to summarize, if we want to be able to model gamma ray bursts, we have to consider physics that spans huge swaths of scales, both in length and time. We have to look at what's happening near the progenitor, so either stellar evolution or compact mergers. And then the actual formation of the compact object, which then launches the jet, which I didn't go too into this time today, but there's a lot of interesting research going on in terms of the jet launching. Then once the jet launches, we have to let it propagate and interact with radiation, and then there's a afterglow, which I really didn't even talk about at all. And at each one of these steps, we have to resolve it enough so that we see all the interesting physics. So I'm going to now talk a little bit about how the general computational setup that we use to approach these problems, and kind of how I think we could try to do this a little more efficiently with different kinds of hardware. And yeah, so the basic idea is when you solve numerical hydrodynamics problems, is you solve conservation equations. So this equation here, this Q could stand for mass, it could stand for momentum, it could stand for energy. This F of Q is basically a flux, so how much of Q is going through a surface, and this S is a source function. So if there's no source function, then there's like nothing introducing mass into the system, or whatever Q is. If there is a source, there's a method, a possibility for something to be injected into the system. So the time derivative plus the divergence through a surface of the flux should be 0 if there's no source. If there is a source, then it's whatever the source is. The way this is written, it kind of makes it not quite as easy to see as if I, put up like the continuity equation, which is a well-known equation that describes mass conservation in a fluid. I could put up the Euler equations, which describe conservation of momentum in a fluid. But with the way it's written here, you see that Q is a vector or an array, Q1, Q2, all the way to Qm. Q1 could be mass, Q2 could be velocity, Qm could be energy, depends on the kind of hydrodynamics you're solving. So what this is saying is that not only is, say, mass conserved in this way, but m quantities are conserved in this way, and each one of them is independent. So you can go about parallelizing it because each of these equations is independent from one another. And up here is a formulation of what's called the Riemann problem, which is a way of discretizing fluid equations and solving them on a finite volume. And what this tells you is that not only are the quantities themselves independent that you can go about solving independently, but each volume is independent, so you can parallelize the grid itself. And here I have a grid. At each one of these grid points, this equation is going to be obeyed, and you can use this method to solve what the next time step of Q, again, Q could be mass, velocity, whatever, the next time step of what it's going to be, and each one of these grid points is going to be independent. Or it's going to depend on the grid cells adjacent to it, but that's it. So you can still parallelize it. Instead of having one grid cell, one calculation per grid cell, you have, in a 2D case, you have 4 calculations you have to do. In 1D, it would be 2 calculations. In 3D, it would be 6. Yeah, 6. So once we have the problem split up, problem laid out and parallelized in principle, we look at hardware and we put the data onto a particular computer, parallelize it, and run it. In the past, that has been a pretty straightforward process because all you really had were CPUs. And the software stack to parallelize CPU hardware has been standardized for quite a while. That was a little more complicated with GPUs, which if you're an astronomer, not a lot of people know how to actually program on a GPU, which makes being efficient difficult. And these days, not only do you have CPUs and GPUs, but you also have tensor processing units, you have neural processing units. I'm pretty sure they're almost the same, but I'm not 100% sure. I think they really just help you bake matrix and tensor operations into hardware. So there might be some differences, but the general idea is to not just do SIMD, which GPUs can do, but more advanced matrix calculations just baked into the hardware. So that would all be one thing. If you had one computer with one kind of hardware configuration and one software stack. But I don't know about you guys, but anytime I run a simulation with valuable cluster time, I really do not want to waste cluster time. So I spend a lot of time on my personal computers, either my laptop or a workstation I have at work. Scale things up there before I put it on the supercomputers, and that makes things even more complicated because on the personal computer side, hardware-wise, it's not just Intel or AMD anymore. You can have Intel or AMD processors. Now you can have Apple Silicon processors. Those have their own GPUs with their own design. And on the non-Apple side, you have NVIDIA GPUs and AMD GPUs, and Intel has GPUs too. And then if you go on the supercomputer side, you don't really have Apple anymore, but you still have to consider whether it's a CPU oriented cluster, a GPU oriented cluster, and what the different hardware is on that cluster as well. Then if you look on the software side, if you want to actually use all of this stuff, regardless of what hardware or platform you're on, you have to use different APIs to actually implement things on the hardware. So Apple has Metal and MLX. Non-Apple platforms have JAX and CUDA, and then OpenMPI, MPI, OpenMP, OpenACC, OpenGL, and OpenCL are pretty. These two at least have been around for a while. So these OpenACC is relatively recent, I think. But they're all different ways of handling parallelized calculations. So what I would like, the way I would like to see things done in the future is to not just take simulation data and put it onto like write software in a way so you can only use it on one platform, but to plan things in a way so that you have your simulation data, you can put it on a computer, and that computer can bring it to and from different coprocessors and different hardware. So it can start off as a CPU process. If it has useful work to do on a GPU, it could send it to a GPU. And CPUs also have specialized hardware extensions to handle vector processing and sometimes even matrix acceleration on the CPU chip in addition to the GPU. So this slide is just to talk about, for me to talk about some considerations about the differences between CPUs and GPUs. The main thing I want to talk about, I'm not sure how much, I'm almost out of time. So what I'm going to focus on is the difference between precision that may or may not exist on CPUs and GPUs. If you have a CPU, it's going to have native support for 16-bit precision. If you have a GPU, that's not always the case. On the new Apple Silicon, GPUs can only support 32-bit precision. Big cluster and workstation class NVIDIA GPUs can do 64-bit precision, but I don't think that consumer class GPUs have native hardware 64-bit precision. NVIDIA, the CUDA stack will let you emulate 64-bit precision on the software side, but that comes at a cost. So when we're doing calculations, if we want to use as much of the GPU and CPU as possible, we need to think about what operations actually need that precision. In my case, if you're actually calculating what the hydro variable should be, so density, pressure, velocity, you absolutely need 64-bit precision. But if you want to do something like adaptive mesh refinement, which is a way of estimating how much resolution we need in a given spot on the grid, we might actually not need the 32-bit, the 64-bit precision in that case, because it's kind of a rough way of estimating it anyway. So this last slide is just talking about the software currently available that could help this happen. There are auto vectorization options in a lot of compilers, but auto vectorization is a difficult problem. And if you just have a loop and tell GCC to auto vectorize it, it's not always clear how successful that's going to be. Another way to go about it is to use existing low-level functions like BLAS and LAPACK. I say this because they're very optimized for the hardware they run on. They've been around forever. So if you can formulate your problem in a way that can do SIMD instructions with BLAS or LAPACK, it's a lot more portable for hardware, to the extent that there's even CUDA BLAS, which is for GPUs. So if you do something with CPU BLAS on one platform and you want to put it on a CUDA NVIDIA card on a cluster somewhere, I think at least it should be easier to bridge this gap than it would be to completely reevaluate the problem. And I think I'm slightly over time, so I'm just going to leave the conclusions up and I'll be happy to answer any questions.
Thank you. Great. Thanks. That was a really good overview of some different approaches.